Theorem 6.2 is the AEP for strong typicality, which says that there exists eta greater than 0 such that eta tends to 0 as delta tends to 0, and the following hold. First, if x is strongly delta typical, then the probability of x is lower bounded by 2 to the power minus n times entropy of x plus eta, and is upper bounded by 2 to the power minus n times entropy of x minus eta. Second, for n sufficiently large, the probability that a random sequence x is strongly delta typical is greater than 1 minus delta. Third, for n sufficiently large, the size of the strongly delta typical set is lower bounded by 1 minus delta times 2 to the power n times entropy of x minus eta, and upper bounded by 2 to the power n times entropy of x plus eta. Note that the form of the strong AEP is very similar to the form of the weak AEP, and the interpretation is also similar. We are going to discuss the proof for each part of the strong AEP. Here we first give the proof idea for the first part. If x is strongly typical, then the empirical distribution is quote-unquote about right. If the empirical distribution is about right, then everything else, including the empirical entropy, would be about right. That is, minus 1 over n times log of the probability of the sequence is approximately equal to the entropy of x. This is equivalent to the probability of the sequence being approximately equal to 2 to the power minus n times the entropy of x. Let us now prove the first part, that is property 1 of the strong AEP. For any sequence x which is delta typical, we have p of the sequence x equals p of x1 times p of x2 all the way to p of xn. And this can be written as the product of all x in the support of x, px to the power n x semicolon sequence x. Here, we only need to take the product over all x in the support, because the number of occurrences of x in the sequence is equal to 0 for all x not in the support. And therefore, we see that the probability of a typical sequence is always strictly positive. Then we take the logarithm of the probability of the sequence. This is equal to the logarithm of a product over all x in Sx. And so, it is equal to summation x log of px to the power n x semicolon sequence x, which is equal to n x semicolon sequence x log of px. Note that we adopt the convention that summation x means summation x in the support Sx. Now we deliberately subtract the quantity n times px and add back the quantity n times px so that we have done nothing. Now we multiply n times px to log px to obtain n times summation x px log px, and then multiply n x semicolon sequence x minus n times px to log px to obtain minus n summation x 1 over n x semicolon x sequence minus px times minus log px. Note that we have divided everything through by n, and then we multiply everything by n. And also this minus sign and this minus sign cancel with each other. Now summation x px log px is just minus the entropy of x. So we can write minus n times entropy of x, and for the other summation, we simply copy it over. Since x is delta typical, summation x, the absolute difference between the relative frequency of x and the probability of x, is less than or equal to delta. Now consider this summation in equation 1 and take the absolute value. By the triangular inequality, this is upper bounded by summation x, the absolute difference between the relative frequency of x and the probability of x, multiplied by minus log px. Now minus log px can be upper bounded by minus log minimum over all x in the support p of x. And this summation, by the assumption that x is delta typical, is upper bounded by delta. For log minimum x px, we just copy it over. Now we call this upper bound eta, and obviously this is greater than 0. So we have proved that the absolute value of the summation in equation 1 is less than or equal to eta. Therefore, the summation is lower bounded by minus eta and upper bounded by eta. This is illustrated in equation 1. Now it then follows from equation 1 that log of px is lower bounded by minus n times entropy of x plus eta, where this lower bound is obtained by taking the upper bound eta on the summation in equation 1. On the other hand, log of px is upper bounded by minus n times the entropy of x minus eta, and this upper bound is obtained by taking the lower bound minus eta on the summation in equation 1. So, we have the probability of the sequence x is lower bounded by 2 to the power minus n times entropy of x plus eta, and upper bounded by 2 to the power minus n times entropy of x minus eta, where eta, defined as minus delta log of the minimum over all x in the support px, where this logarithm is a constant, tends to 0 as delta tends to 0. And this proves property 1. Let us now discuss the second property of the strong AEP, which says that for n sufficiently large, the probability of getting a strongly delta typical sequence is very close to 1, specifically greater than 1 minus delta. The idea of this property is actually very simple, although the details of the proof is a little hairy. Basically, by the weak law of large numbers, with probability tending to 1 as n goes to infinity, the empirical distribution of the random sequence x is close to the true distribution px. And so by definition, x is strongly typical. The proof goes as follows. To prove property 2, we write nx semicolon random sequence x equals summation k equals 1 up to n b sub k of x, where b sub k of x is an indicator random variable which is equal to 1 if xk is equal to x and 0 if xk is not equal to x. So bk of x tells whether xk is equal to x or not. And the summation k equals 1 up to n bk of x simply counts the number of occurrences of small x in the random sequence x. Then bk of x, k equals 1 up to n are IID random variables, because x1, x2 up to xn are IID random variables. Specifically, the probability that bk of x equals 1, that is xk equals x, is equal to p of x. And the probability that bkx equals 0 is equal to 1 minus p of x. Note that the expectation of bk of x is equal to 1 minus px times 0 plus p of x times 1, which is equal to p of x. In general, the expectation of an indicator random variable of an event is equal to the probability of that event. Now, by the weak law of large numbers, for any delta greater than 0, and for any x in the alphabet, we have the probability that's the absolute value of 1 over n summation k equals 1 up to n bk of x, namely the average number of occurrences of the value x in the random sequence x, minus px, the probability of occurrence of the value x, greater than delta divided by the size of the alphabet, is less than delta divided by the size of the alphabet for n sufficiently large. In other words, the probability that the relative frequency of x deviates from the true probability px by a small amount is very close to 0. Then, the probability that the absolute value of 1 over n of x semicolon x minus px greater than delta divided by the size of the alphabet for some x, by our definition, is equal to the probability that the absolute value of 1 over n summation k equals 1 up to n bk of x minus px greater than delta divided by the size of the alphabet for some x. Now this is the probability of a certain event for some x, and hence we can write this as the probability of the union of the event over all x. Now, by the union bound, which says that the probability of A union B is upper bounded by the probability of A plus the probability of B, we obtain the upper bound summation x, the probability of the event for a particular x. Now the probability of this event for a particular x is upper bounded by delta divided by the size of x. And so we have summation x delta divided by the size of x. Because the number of terms in the summation is exactly equal to the size of x, this is equal to delta. Now, the event summation x absolute value 1 over n x semicolon x minus px greater than delta implies the event absolute value 1 over n x semicolon x minus px greater than delta divided by the size of the alphabet for some x. Let us mark this event in yellow and this event in green. Then we have the probability of the yellow event is upper bounded by the probability of the green event. Therefore, the probability that x is strongly delta typical, which is equal to the probability that summation x, absolute value, 1 over n of x semicolon x minus px less than or equal to delta is equal to 1 minus the probability that this summation is greater than delta. And this is the yellow event. And so, this is greater than or equal to 1 minus the probability of the green event, which we have shown is less than delta. And therefore, we have obtained the upper bound 1 minus delta. This proves proposition 2. Property 3 of strong AEP says that for n sufficiently large, the size of the delta typical set is approximately equal to 2 to the power n times the entropy of x. The proof of this property follows from property 1 and property 2 of strong AEP in exactly the same way as in theorem 5.3. So we leave this as an exercise. Theorem 6.3 is a stronger result, which says that for sufficiently large n, there exists some function phi of delta, which is strictly positive, such that the probability of not getting a strongly typical sequence is less than 2 to the power minus n times phi of delta. This means that this probability not only tends to 0 as n tends to infinity, but it tends to 0 exponentially fast. The proof of this theorem invokes the Chernoff bound. Since we are not going to use this theorem for the rest of the course, we omit the proof here.